Hey everybody, this is the second installment of our video project for the Inorganic Chem class. It is a material characterization presentation on powder X-ray diffraction. We got a lot to get through, so let's jump on into it. To begin, we're going to look at a general outline to kind of guide us through the presentation. We're going to start off with X-ray diffraction and the different concepts that play into that and how they're going to fit into the grand scheme of things. From this, we kind of move into reflection. It's part of X-ray diffraction, but it's a little bit different way of thinking about some things. With reflection in mind, we can move into Bragg's equation and how we get that and how that's going to relate itself to powder X-ray diffraction. Next, we're going to move into powder X-ray diffraction itself and see the different ways we can use it, what we're using it for, and how it works. Then we're going to finish with a case study. We're going to look at bismuth. It's kind of an inorganic one, and how powder X-ray diffraction is used for analysis within that case study. Alright, so jumping into it, we have a background on kind of X-ray diffraction and what it is. More or less what we're looking at is an interference of an actual direct beam across a sample. So as we can see over here on the right, what it is their beam comes in, and when it hits our sample, it's then diffracted or reflected into different areas, which is then picked up on by a detector. This is looked at as the concept of a scattering effect, and another possible way you can kind of think about it is a reflection off of your sample and what those outcomes are. So, getting into reflection a little bit more, there's a couple of concepts we're going to look at. The main one being is that all energy through the main beam, or however we're going to do it, is always going to be retained. The intensities and the energies coming off of the sample could vary a little bit, and that's going to warrant different levels and peaks and different things we'll see later. The second thing we want to look at is distance, and there's two types of this. There's the distance from the sample to the detector itself, and then as we're going to see a little bit later, there's going to be another type of distance between two parts of a sample. The next thing we want to look at is phase. Now the beam that we're looking at is always coming in the concept or the form of a sine wave, so phase is a big piece of this. We have constructive, which is when two different sine waves are coming together to form a bigger wave, and then destructive. When two waves are out of phase, they actually nullify each other to get a zero. The other one that's really big and important in powder X-ray diffraction is going to be angles. Angles play a really large part of this, which we're going to get into in a little bit. For understanding reflection and angles and how distance and angles themselves play a really big part into this, we're going to look at this kind of diagram. Some of the big things to look at is, as I mentioned, there's the two types of distance. We're going to be looking at the distance that's between two planes, so we have an upper and a lower plane, which is going to be our D, and the angles. So we have our incident beam coming in and creating a contact angle, and then we have the angle that we're going to be using for a lot of our measurements, which is this inside angle that's kind of found through the law of congruent angles. We're not going to get into all of that. Just know and take away that this is the angle we're actually going to be looking at. It's formed by two different perpendiculars. How this is kind of working and what we're looking at is the incident beam coming in and then being reflected off of our sample. To note is because we're using two different planes and looking at two different pieces of this, we have two opposite beams. This is where that ultimate kind of law of science coming in, where if we have two beams being reflected that are in phase with each other, we see a lot bigger intensity. Now, how does this kind of work when we get a couple more planes coming in? Now, when we introduce more planes, we kind of see it with increasing intensities or decreasing intensities depending on the actual sample we're looking at. And this is where we're going to start to move towards powder X-ray diffraction or X-ray diffraction as a whole in itself. But before we get there, we're going to look at the concept of Bragg's law. So, Bragg's law, or Bragg's equation as it's commonly referred to. What it is basically 2d sine of theta equals n times lambda, as you can see. Some of the features that we kind of see coming out of it conceptually is the angle and how that plays a big role. As we just saw, angle is that inner angle that we want to look at, and it's dependent on the way your beam goes in and the way your beam is reflected. Intensities are another big kind of thing that we see out of it, which we're going to see a little bit later in the case study, and the intensities come from that lambda component, and oftentimes they give us different peaks in our readouts. The last big feature about Bragg's law is it's very, very unique dependent on the sample that you're looking at. It's one of the big concepts and the reasons why that using Bragg's law and powder X-ray diffraction works so well. So breaking down the equation a little bit, we obviously know 2 is a number. D is that distance between the planes of the crystallites that we're going to be looking at. The sine of theta, obviously, as I just mentioned, is going to be that inner angle that's created by the perpendiculars. N is the integer, and that's dependent on the amount of layers that we're actually have in our sample. Lastly is lambda, which is our wavelength, and that's going to be related to intensities later on. Moving right along, we're going to start to look at powder X-ray diffraction itself, or powder XRD for short. One of the big things with powder XRD is that it's a polycrystalline sample analysis technique. Ultimately, what this is talking about is that we're going to look at crystallites, which are the very, very minute pieces of our sample, and we're looking at multiple of them. Now, one of our friends is going to be looking at a single crystal technique, I believe. But moving along, as I mentioned, these crystallites are the little minute details of our sample. And if you're paying attention in the outline, there was a photo of kind of circle-esque things. Now, as we've been looking at and discussing, is as these beams come in, they reflect off of our sample, and they give us an output. That output actually, if you look at it as a whole, comes out in the form of a cone. The way we test these is by using a powder diffractometer, as we can see over on the right. Now, Bruker Scientific is a team or an organization that makes a lot of these, and how it kind of works in the way we've been looking is our component on the left emits our beam, which comes in and hits our sample plate, which is then reflected and picked up by our reader. On a more scaled down approach, this is what the Bruker machine is doing. How it's set up is on our left, as I mentioned, we have our X-ray tube, or our emission source, that kind of rocks back and forth on a circular path. This allows us to change the incident beam optic angle, which we can see right here, and that's the angle that's impacting on our sample. From here, the sample then reflects or diffracts the beam into our detector. As I mentioned before, the detector can also be called a reader. Kind of depends on what you're looking at. I've seen it both ways. This detector also moves back and forth on the similar path, and that's just so that it can pick up all of the different beams that are emitted off of it. Now, the detector then takes all of this into account and emits off or gives us a different reading for each of the samples that we're looking at. Now that we've looked at what powder XRD is and how it's kind of working, we can ask the question, why? Some of the techniques that people are looking at doing using powder XRD is identifying unknown materials. We can also look at the determination of sample purity. This is usually seen through intensity and comparing it to known values. Another one is we can look at phase changes and expansion coefficients, and this is a lot more seen in like the crystalline structure and how that plays a part into it. Another, and kind of the last one we're going to look at is the investigation of phase diagrams and new materials. Now, as I mentioned, we're going to look at a case study. That study we're going to look at is mixed bismuth 3 complexes with sulfur donor ligands, and this team uses a lot of different techniques to analyze what they actually did, but powder XRD is one of them. So, getting into their case study a little bit, they were looking, as we mentioned, at bismuth sulfur donor complexes. As we can kind of see over the right, we have a bismuth center metal ion and then a bunch of sulfur ligands around it. Why they were kind of looking at bismuth, and some of the reasons why a lot of people look at bismuth, is it's listed as an antimicrobial. And it's also oftentimes used in different agriculture analyses, in polymer chemistry and medicinal chemistry, based on its antimicrobial kind of components and factors. As I mentioned a little bit ago, the team used a lot of different things in their analysis of their complexes. They used things like NMR, IR spec, all sorts of things, but they also used powder XRD. Also, what I mentioned a little bit ago is we get these different readouts and different peaks. Now, what these kind of look like are a little weird. So, some of the things that they saw and what they were looking at is they wanted to use and test different complexes. So what these are going to be 3 of the spectra that they got for their powder XRD. They all look kind of similar, but they have very, very distinct differences as well. A lot of it comes and shows in this kind of peak angle around the 10. What we can see from this is that the complexes that they assumed to be, and they confirmed through NMR, also gave different readouts for the powder XRD. So these are the type of things that they want to look at, is how changing their angle, which is seen on our x-axis, is actually giving us a different intensity or peak from our powder XRD. Now these are the different things that we look at when we use powder XRD. Alright, so kind of wrapping up, going back over what we looked at. We started off with our X-ray diffractions. We looked at reflection and Bragg's equation and how those played into the grand scheme of everything. Then we moved into powder X-ray diffraction, or powder XRD, and the concepts behind it, that it's polycrystalline analysis. We use a diffractometer to look at it, and then the different applications that we're using it for. And then we finished off with the Bismuth study, where they looked at phase characteristics and size determinations and how those kind of showed up on their outputs and their readings. So that's powder XRD in a nutshell, and thank you.